this is the second half of chapter 6 on bones and skeletons. And today we're going to talk a little bit more about how these bones develop. Now, in general, this process of bone formation can be called by two different names. The first one is ossification, right? Or this will also be used, the term used that can be used for bone formation is also osteogenesis. So if you hear me say ossification or osteogenesis in this portion of the lecture, realize I'm talking about the same thing. I'm actually talking about forming bone. Now, bone begins formation as an embryo and then eventually turns that embryonic skeleton into a bony skeleton. And eventually we have this growth that goes on into early adulthood as far as the length of bones. Now, throughout our entire life, bones can get thicker and they can also repair and remodel just depending on the stresses that are placed on that bone. Now, bone develops by one of two different methods. So these two different methods are intramembraneous and endochondral ossification. So these two types of development is how we eventually get to our complete skeleton that we currently have. Now, with endochondral ossification, the bone replaces the hyaline cartilage that's initially laid down. And this new bone is actually called endochondral bone. Now, intramembraneous ossification is a little bit different, and this bone develops from the fibrous membranes. Now, this particular type of bone is what we call membranous bones. So the formation of the bony skeleton actually happens a little bit before the 8th week, where the embryonic skeleton is more of a fibrous membrane and cartilage. And from that, we eventually develop our actual bone. So as we start to think about how these two processes occur and allow us to form our entire skeleton, we must remember that each one of these processes are happening kind of concurrently with each other, right? So they're happening together. Now, endochondral ossification develops the bones below the skull, excluding the clavicle, which developed in the opposite manner, which was that intramembraneous ossification. So what happens in this process is that the hyaline cartilage is actually broken down and it's kind of used as a guide to have that ossification process proceed. So just think of it as like a scaffolding that we will eventually build a bone upon. Now, what happens is the blood vessels eventually invade the perichondrium, converting it to vascularized periosteum. So if you remember what periosteum, that was the surrounding membrane around the bone. Now, these mesenchymal cells eventually turn into osteoblasts, those bone creating cells, because of that increased amount of nutrition that is getting from the vascularization of that periosteum. So if you can think about what that means is if a cell has more nutrition, it can develop a little bit different. It can develop a little bit faster, and it does develop. And these mesenchymal cells turn into osteoblasts, the bone creating cells, because of that increased amount of nutrition. Now, there are multiple steps in this process of endochondral ossification, and we'll go through each one of these 5 steps, right, and try to understand it better to what actually is happening in that formation of the bony skeleton. So the first step is when we have this bony collar form around the diaphysis. Remember that diaphysis is that shaft of the bone. And the osteoblasts within the periosteum secrete what's called the osteoid, right, against that hyaline cartilage diaphysis. And it covers it in the periosteal bone collar. So what does that actually look like? So if we look right here, we can kind of see that happening, where we see this right here, this bony little collar, and then we have this primary ossification center. Now, what begins to occur is that the cartilage in the center of the diaphysis starts to calcify, right? And this is signaled by the growing chondrocytes. So these chondrocytes begin to grow, and as they grow, they begin to die, because at this point, no blood vessels. If I don't have any blood vessels, it's very hard for me to get nutrition. The only way I can really get nutrition is by diffusing from areas that are surrounding me. Now, this opens up that little cavity in the middle of that bone. And the bony collar around it actually helps to stabilize that developing bone. Now, eventually, around the third month, this periosteal bud begins to form, right? And it invades that cavity. So it starts to invade this cavity that you have developing in it. Now, as we see, this bone is starting to deteriorate, and it was deteriorating because, again, in this step, it didn't have any of that nutrition that is actually being brought by this particular blood vessel right here. So as the blood vessels begin to invade in that area, you also get nerves and other cells that come into that area, and the osteoclasts begin to break down some of the calcified cartilage that is within that matrix. Now, at this point, the osteogenic cells turn into osteoblasts. Remember, osteogenic cells are just cells that can kind of differentiate into other types of bone cells. And this is why this is a stem cell. So it's a bone stem cell. Now, the osteogenic cells begin to develop into osteoblasts. And as they do this, they start to secrete that osteoid. Now, what eventually happens is the osteoclasts break down that newly formed spongy bone. So if we can look right here, we can start to see some spongy bone starting to form. Well, the osteoclasts break that down, right? And they extend that medullary cavity up. So it gets larger and larger, and this is actually increasing in the length of that bone. Now, the secondary ossification centers start to form. And how do they form? Well, they form because they start to get these epiphyseal blood vessels. Remember, the epiphysis are on the end. The diaphysis is that shaft of the bone. Now, as they start to do this, the cartilage begins to calcify and then it deteriorates much like it did within that primary ossification center. The cartilage then calcifies and deteriorates and then allows the periosteal bud to invade, similar to what we saw in the previous steps. Finally, the epiphysis ossify. Now, it depends on what type of bone we're dealing with. Realize that we do have different types of bones. We went over long bones, short bones, flat bones, irregular bones, right? And sesamoid bones, right? As we start to look at this, in short bones, only that primary ossification center forms. Now, when we look at things like irregular bones, we may have multiple primary ossification centers, and this is why it gives it that irregular shape. Now, the spongy bone is eventually retained in the epiphysis, and this is how you develop that long bone. And this, again, is endochondral ossification. Now, this differs quite dramatically from what we see when we look at intramembraneous ossification. So this process actually forms the bones of the cranial bones and the clavicles. So it's mostly flat bones that this creates. And this is about at 8 weeks or so that the fibrous connective tissue is formed by those mesenchymal cells. Now, as we go through this, I really want to make sure that you understand what's going on. So I really want you to look into your books, and they have this great diagram. I will show it here, but as you're studying, I want you to really focus on this diagram to show you the difference between that intramembraneous ossification as well as that endochondral ossification. All right, so let's take a look at what's going on. So in this first step, we have this ossification center appear, right, in that fibrous connective tissue. So here you can see it form, right? Now, the second step, what we have forming is the osteoid. So the osteoid starts to be secreted within the fibrous membrane, and then it calcifies. Now, that bone, right, starts to form, and this is spongy bone, right? And it forms from that periosteum. So that periosteum that's on the outside, right? And finally, the lamellar bone replaces that woven bone just deep to the periosteum, and then that red marrow begins to appear, right? So this process is a little bit different than what we saw with the endochondral ossification, but both of them are actually necessary in order to develop a full skeleton. Now, just because we're born doesn't mean our skeleton stops growing. It should be kind of apparent that you aren't the same size that you were always, right? Especially when you were born. So we keep growing. So we have this postnatal bone growth, right? And now the long bones are lengthened through this process called interstitial growth, while the thickness of bones actually comes from what we call appositional growth. Now, I know you may have heard before that people say, well, I'm not big, I just have big bones. So it is possible to get thicker, bigger bones. So how do you get this thicker, bigger bones? By impact, by the things you do with your body. And generally, as bones get longer, they also grow in thickness. Now, most of the bones of the body actually do stop growing after adolescence. It's this particular period of time where we have this epiphyseal plate that eventually seals the epiphyseal line. This epiphyseal plate is in between the two epiphyses and that diaphysis, that shaft. And I'll show you a picture of this in just a second. Now, there are some bones that continuously grow throughout an entire life, and those would be like the bones of the nose or of the lower jaw. Now, as we go and look at this bone growth, this interstitial bone growth, remember we're going to grow in bone length, there are these different zones, right? So long bone growth, right, is occurring mostly on the epiphyseal end, right, of long bones. Now, at the very end of that long bone, we do have this area called the resting zone where we don't have a lot of growth. But if you can imagine, under that, as it begins to develop and put more cells there, then it kind of pushes that end up. So as we start to look at these different zones, like this resting zone here, it's not a lot of mitotic activity. This means we don't have a lot of cellular division going on in this area. Now, where we do have a lot of cellular division is in what we call this proliferation zone. So in this proliferation zone, we're actually pushing up the epiphysis away from the diaphysis. So if you think about this bone right here, right? So if you take a look at this bone, you'll see that epiphyseal plate, right? This is kind of a section of that. So that resting zone, the area at the very top of that, wouldn't be doing much, but right under it, that proliferation zone is where those cells are rapidly dividing, right? Rapidly dividing. Now, as they rapidly divide, eventually what happens is some of those older cells, those older chondrocytes, begin to stack and enlarge. And as they enlarge, they actually leave these interconnected spaces within them, right? Now, what happens with these spaces is they begin to get surrounded by this cartilage matrix that begins to calcify. So this is what's happening in the calcification zone. These cells are beginning to die, right? And as they die, they produce this calcification zone. Now, the last zone right here is the ossification zone. So after they calcify, right, and they've been mineralized, then what we have is these long spicules of calcified cartilage that is left, and they begin to ossify. So the osteoclast and osteoblasts kind of take turns breaking down and building up these little spicules until eventually it replaces them with spongy bone. And ultimately, that spongy bone leads to the lengthening of that medullary cavity and the lengthening of that bone. So this is how long bones develop and grow. Now, it isn't all about long bones. We also have other types of bones as well. And we will get to those and see how the thickness of the bone actually does change. Remember, that's the difference between interstitial bone length and appositional bone thickness. Now, eventually, we all do kind of stop growing in bone length, right? Now, that doesn't mean bones stop growing. Bones are in this constant remodeling phase. So depending on what you're doing with your life and your body, right, your bones will change to kind of suit what you're asking it to do. Now, that epiphyseal plate eventually becomes thinner and thinner and is eventually replaced by bony tissue. Now, this happens at different time periods depending on your sex. So for most females, it happens around 18. And for most males, it happens around 21. And this is when that epiphyseal plate closes and eventually turns to an epiphyseal line. Now, how do you gain in bone thickness. Well, this is again that appositional growth. So appositional growth is possible throughout your entire life. And it's dependent on the stresses, the weight, and the exercise that you have done within your life. Now, bones have a tendency to get thicker as they get longer. So how is this actually happening? Well, what's happening is the osteoblasts will actually secrete a matrix on the surface beneath the periosteum. And as osteoclasts and the endothelial surface break down, then we actually make more bone internally. So it's kind of like we're building up, right? So we build up. Well, sorry, when building up exceeds breaking down, then that bone is actually going to get thicker. Now, all of this bone growth and bone remodeling is actually controlled by hormones. So these hormones come from areas like the thyroid or the anterior pituitary. So the thyroid hormones actually help to regulate hormones, growth hormones that come and originate from the anterior pituitary. Now, this is initially. Now, once we hit puberty, something changes. We have these two hormones that kind of come into play that kind of guide our growth at that period. These two hormones are estrogen and testosterone. Now, they control that growth through adolescence until we reach the end of adolescence and that epiphyseal plate seals to that epiphyseal line. Now, whenever you have excess or too little of these hormones, this is usually when we have some type of abnormal growth of the skeleton occur. As we move on to bone remodeling, we must realize that the skeleton that we normally kind of associate with being dead, I mean, we even have a skull and crossbones that kind of signifies something or it signifies death, right, is the furthest from dead. Right? It is our lasting legacy. This is the thing that will still be around as all the muscles and other tissues of the body kind of decay away and is eaten by different microbes, but the bones stay around. But bones are the furthest thing from dead. Just think about everything that we've talked about to this point and the way that these cells are constantly breaking down and building up. There's a lot of mitotic action going on in bones. So bones are very, very alive. In fact, they have a great capacity to repair themselves when damaged. So we should think about bone maybe in a little bit different way. Now, as we start to understand this remodeling, we have to realize that there are two different types of cells that are involved in this process, right? The osteoclast and the osteoblast. Remember, those osteoclast are the bone destroying cells, while the osteoblasts are the bone creating cells. And it's going on so much, and this turnover is so high that about every 3 to 4 years, you actually replace all the spongy bone in your body. And in about every 10 years, you replace all that compact bone in the body. So you're constantly depositing bone and resorpting that bone, right? Depending on the needs of that body and the impact that you place upon your bones as well. Now, if this does not occur, right, this whole remodeling process, we do run into some issues. And one of the major issues is that these calcium salts begin to crystallize, and the bones that they are crystallizing in become extremely brittle, and they have a much, much higher tendency to break. So this constant deposit and removal is very necessary to the stability and strength of the bones. Now, where does this all occur? Well, in adults, that deposit and removal of bones happen both at the junction of the periosteum and the endosteum, right? And this process is just what we call remodeling. Now, as we start to think about how we break down these bones and how we resorb these bones, we have to realize that these cells are very important. The osteoclasts have this ruffled edge, and they cling to the bone and they kind of dig grooves into that bone and they secrete multiple things. One of those things is hydrogen ion. If we just think about what hydrogen ion is, we talked about hydrogen ion being a measure, the amount of hydrogen ion being a measure of how acidic something is. So essentially what they do is they dump acid in there along with lysosomal enzymes, which can help to further break down that bone cells or those bone cells. Now, as it breaks them down, the cells in the matrix are absorbed, all right, by this process that we call endocytosis, taken into the cytoplasm and then transported across the cell by a process called transcytosis. And once it's released to the other side, the osteoclasts are dumping that material, that demineralized bone, calcium, phosphate salts, into the blood. Now, osteoclasts don't just keep doing this. After they do this process, they have a tendency to run through this process that we call apoptosis, which is a programmed cell death. So they essentially just take themselves out. Now, the other process of depositing bone actually happens at this area of the bone that we call the osteoid seam. And this is where the osteoblasts deposit new matrix. Now, it takes about a week for that osteoid to actually become calcified. So as those calcium and phosphate salt ions increase, it actually makes these little crystals form. And from these crystal formations, we can actually mineralize that bone, right? So it's very important to realize that it's not only that, but also other things like enzymes like alkaline phosphatase that is also involved in this mineralization process. So there's a lot of things that need to occur in order for you to actually deposit bone. Now, there are some things that can help in causing an increase in that bone depositing. So mechanical signals, just simple force. The more force you apply to that bone, eventually the bone's going to get thicker, right? The amount of concentration of calcium phosphate salts, right? Also, these proteins that bind and concentrate calcium. So there's many different factors that go into binding and creating that very dense bone. Now, another factor that goes into this remodeling process is simply hormones, right? Hormones control our body to a great degree. The other way we control our body is by our nervous system, but hormones are very important because they generally act slower, but they act for a much, much longer duration. So as we start to think about what's occurring in this process, right, we have to realize, well, why do we even keep calcium phosphate salts in our bones besides making them hard? Well, it's because we need that calcium. That calcium has a tremendous amount of function in the body. Everything from nervous signal transmission to muscle contractions to ability to clot blood, all kind of arrive because of this level of calcium that is within our blood and the use of that calcium. So if you don't have that calcium, a lot of the functions of the body is disturbed. So it kind of behooves us as humans to keep a large amount of this calcium around. And where do we keep this calcium? We keep it in bone. And when we need it, because our calcium levels in our blood drops too low, we can simply just demineralize that bone and acquire that calcium from that bone. So what we see here is this kind of feedback loop. So as the calcium level drops, we have this hormone called parathyroid hormone. Right. And it should be obvious where this parathyroid hormone comes from. It comes from the parathyroid gland. And it's in response to the lower levels of calcium within the blood. Now, as parathyroid hormone goes up, it actually stimulates those osteoclasts to do more resorption. So that means it says, hey, I'm going to break down these bone cells because they have the stuff that the body needs. Now, as calcium levels go up, the amount of parathyroid hormone goes down. That means the osteoclast activity goes down. Now, there's another hormone out there called calcitonin, which we really don't understand what it does at normal physiological levels. But when you increase or greatly increase that dose, right, then what happens is the amount of calcium in the blood does go down, right? But that's not a natural occurrence. That's usually by way of some type of medical treatment that was given. Now, if the blood calcium remains low for extended periods of time, then osteoclasts will continuously demineralize that bone to the point where it actually forms holes in that bone. So if you know anything about what I'm talking about, if you keep demineralizing, you're putting holes in bones, you think about what that prefix for bones is, osteo, and then we talk about holes, we may say pores. So bone pores. What's that name for that? Yeah, it's called osteoporosis. So that excess of calcium within the blood actually causes you to be non-responsive. So let's think about that. If you have too much of this calcium, then your muscles, your nerves won't respond as they should. Now, the opposite of that would be extremely low levels of calcium, which would have hyperexcitability. Like everything would cause nervous signals to be sent or muscles to twitch, right? Which you don't necessarily want as well. So we have to have this kind of fine control of the amount of calcium that is within our blood. Now, there are some other hormones out there that do help to control the way bone reacts and the density of that bone. One of those is leptin, right? We don't understand exactly how it works, but it does do something to help regulate that bone density. Other hormones that are released by areas like the gut, called serotonin, may cause you to retain calcium in bones when new calcium is actually introduced to the body by way of things like diet. Now, there are other factors that do come into bone density. One of those factors is just simply mechanical stress. If you pull on bones with muscles by way of that tendon, it will strengthen that area that you are pulling or acting upon, right? And this goes into what we call Wolff's Law, where bones grow and remodel based upon the stresses that are placed upon them. So if you think about this, the more stress we put on a bone, the denser it becomes. It reacts to what we do. So if you want thicker bones, you want stronger bones, one way to get it is simply by just putting more stress on it. And this is a reflective of Wolff's Law. Now, if we look at this bone right here, what we see is we have two different areas. One area where we're getting outward tension, right? One area where we're getting inward tension. And this is why we see bones like this, right? And this is the femur, where it has this kind of bow to it. And that bow is because of the forces that we place upon it, right? That force that we place upon it guides and directs that bone. So if we have some issues with bone, right, and we see that bone isn't taking the shape that we want, it's because of the stresses that we are putting on it. Now, this also accounts for other things like the handedness, why certain pieces of the bones are stronger or larger than other bones. So this Wolff's Law explains a lot about the way bones are. Just think about it. If I'm bedridden and I'm not moving a lot, yes, muscles will atrophy, but think about what muscles are doing. Muscles are there to pull on bones. So if the muscles aren't pulling on the bones, that means not only are the muscles atrophying, but the bones are changing as well. You start to demineralize those bones because you don't have that impact. There's no need. Now, if we take this even further, think about deep space flight. As we go out into deep space flight, those mechanical stresses just simply aren't there, right? You don't have that impact because you're not under that weight of gravity constantly. So bones will begin to change. Bones will begin to demineralize, right? And if we're going to areas where we need to eventually walk, like let's say Mars, by the time you get there, your bones may have been significantly demineralized to the point where when you begin to do activities there, you may easily break those bones. So it's very important to kind of understand that as we start to plan these trips, we have to have ways to maintain that impact to bone. Now, one way that has been devised is actually by electrical current, right? And this is so interesting. Electrical current actually is caused by the deformation of bone as we put that impact on that bone. But if we can simulate that electrical current without that impact, maybe we can still help ourselves to maintain that bone density as we go deeper and deeper into space, or just have individuals that may be bedridden, or we have individuals that may be in that repair process of repairing bone. Now, when we think about repairing bone, it's kind of inseparable. You have to first break that bone. So those breaks are just called fractures. Now, depending on where you are in life, most young people are going to usually get fractures because of something that they were actively doing, maybe playing the sport, falling off something, an accident, right? Usually trauma. As you get older, right, you can still have those same things occur, but usually the bone breaks don't come from that type of trauma. Usually the bone breaks occur because your bones are actually becoming less dense, right? And that density is important. Now, there are different ways to classify these fractures. Bone breaks have an amazing capacity to repair, but the fractures and how we kind of talk about the fractures is what we want to kind of focus on right now. Now, fractures are classified in multiple ways. One, by the position of the ends of the bones when they break. Two, by the completeness of the break. Is it all the way through, only partially through? Does it break the skin? And finally, the location, external appearance, and then the nature of the break. So if we start to think about this, right, and we look at the position of the bone, displaced means that those ends aren't in a normal alignment. Non-displaced means they have that normal position, right? Complete is, did the bone completely break all the way through, or is there still a little piece that's kind of hanging on of that bone? And then also whether it is open or a compound fracture that actually comes out the skin, or closed, being a simple fracture that didn't penetrate that skin. So as we start to look at these types of fractures, I want you to kind of get used to using these terms like this one, this comminuted fracture, right? If you have three or more pieces in a fracture, it is a comminuted fracture. Now, there can also be compression fractures, and we see this in areas like the spine, where so much force is being placed down on that bone that it just kind of shatters, right? And then we have a spiral fracture. A lot of times we see this spiral fracture from twisting. So you can imagine if I'm playing a sport like soccer and I plant and I twist in order to kick, and it's too much tension on that bone, right? And it fractures, that will be a spiral fracture. And they kind of have these characteristic shards that you see when you have a spiral fracture. Epiphyseal fractures do happen, and they usually happen right on that epiphyseal line or that epiphyseal plate. Right? When we look at depressed fractures, it's usually because we have some blunt object. So if you look right here, this is a skull fracture, where you can imagine where we have that dipole, where we have the compact bone, spongy bone in the middle, and compact bone on the other end. But if you smash that in, that would be a depression fracture. Green sticks fractures are incomplete fractures, so they don't go across the whole bone. So you can imagine if you kind of broke a branch off a tree, but it didn't totally come off, part of it is still connected. That is similar to what we look at when we look at a green stick fracture. So in order to fix these fractures, we have to do something. So what we do is what's called a reduction, and that's the realignment of that bone. Bone will heal itself. Right? You just have to place it in the right orientation so that it heals properly. Now, if you don't, it will still heal itself. But a lot of times when it heals itself, there is some displacement of that bone. So you may get some abnormalities in the way that the skeleton looks when it's repaired because of that improper placement. Right? So reduction is that realignment. Now, after you realign it, you have to immobilize it. Right? And typically it takes about 6 to 8 weeks, depending on who you are. Like younger individuals, about 6 to 8 weeks. Longer if there is an elderly individual involved, or if it's like a weight-bearing bone. Now, there's 4 steps in that repair process. That first step is the formation of that hematoma. Now, the hematoma forms because blood vessels are torn and they begin to hemorrhage. So blood begins to kind of pool in that area. Then blood clots begin to form. And when blood clots form, you no longer have that blood flow. So no blood flow, no nutrition. All right. And when you don't have nutrition, cells eventually begin to die. Right. And then you have the normal classic things that go along with breaks, like inflammation, swelling, pain, and all those other things that we have a tendency to hate. But it is necessary in this whole bone healing procedure or process. Right. So here you see the hematoma formed. You see this blood and all this blood pooling. And the reason why, again, is because blood vessels broke. Whenever blood vessels break, our body always seeks to kind of clot that blood and prevent that blood loss. Now, the second step is the formation of a fibrocartilaginous callus. So in this process, capillaries begin to grow through that hematoma. And as they begin to grow through that hematoma, they bring with it something. Well, what comes is white blood cells, macrophages, and they begin to clean up that area because all that damaged tissue needs to get out of there before I start to reconstruct that bone. Just like if you knock down a building, you wouldn't build a building over the rubble of the old building. You would have to first remove that rubble. And this is the job of those macrophages that are coming to this area by these newly formed capillaries. Then we have these fibroblasts and osteogenic cells that begin to come to this area, and they come in from Obviously, where they could come from was the endo or the periosteum. And as they come to this area, those fibroblasts start to produce collagen. And this collagen connects the two bone fragments. So it's kind of linking them together. Now, they aren't touching yet. They aren't fully formed, but they're setting the stage for that complete bone repair. Now, some of the cells do turn into chondroblasts, and they start to secrete this cartilage matrix. Osteoblasts start to form this spongy bone in this area, and then the cartilage cells furthest from those capillaries start to calcify. Remember, furthest away, I may not have as much nutrition as something that is closer to those capillaries. So they start to calcify that matrix that they secreted, right? At this point, they create that fibrocartilaginous callus. So now we got this nice little callus form, but that isn't the only thing that we need to happen. We need to finish this process, and this is when we form that bony callus, right? And it takes that fibrocartilaginous callus and eventually converts it to a bony callus until it joins those two bones together. And it's very similar to what we talked about when we talked about endochondral ossification. Now, here you can see that formation of that bony callus, but we're still not finished. We have to remodel the bone a little bit, right? To the point where it actually resembles that original bone. After this bone is finished being remodeled, the bone is pretty resilient. That fracture is healed, right? Now, not to say they can't occur again, but it's a pretty strong piece of bone at that stage. So this is the process that we use in order to repair bone. The final portion of this lecture will deal with bone disorders. Now, it should be known that bone disorders can come from a lot of different areas. It can be because of nutrient deficiencies. It could be because of hormone abnormalities, right? And it can even be because of viruses. And that's what we see with some of these diseases that we're talking about of the bone. So the first ones that we're going to talk about are osteomalacia and rickets, and they're kind of associated with each other. And it kind of just depends on your age as to which one of these you would actually acquire. When we look at osteomalacia, it's usually because of poorly mineralized bone. Now, the osteoid is formed, but as it lays down that matrix, it's not actually adding the calcium salts that is needed to be deposited in that area so that those bones can be hardened. So bone has a tendency to remain soft and weak. And this is what we normally see in older individuals. Now, rickets, on the other hand, occurs mostly in children, and that's very similar to osteomalacia and can cause severe disfigurement, but it's usually caused by an insufficient amount of calcium or vitamin D. So if you think about when this might occur, well, if a baby is just born, all right, and the mother's breastfeeding, but the mother is vitamin D deficient, then that means she won't be giving that baby that vitamin D that it needs in order to help to mineralize that bone, right? Or in the case of just not having enough calcium in the diet. So supplements may be necessary in order to help prevent these conditions, right? Now, the next condition that we're going to talk about is osteoporosis. And it's not just one disease, but it's actually a group of disease that actually lowers that rate of deposit and actually increases that rate of resorption. So that means I'm breaking down bone faster than I can actually make it. This makes the bones extremely brittle, right? Not only that, but it also causes the spongy bone, causes the placement of more spongy bone, and that spongy bone is much, much more vulnerable to breaks. So compression fractures are very common, as well as fractures within the hip. Now, there are a lot of risk factors that go into developing osteoporosis. And if we look at this picture here of the normal bone versus the osteoporotic bone, we see those holes. So remember when we talked about bone pores or osteoporosis, this is what it looks like microscopically when we look at those trabeculae. Now, some of the risk factors that are associated with it may seem a little bit weird, but this is what they are. One is just being elderly. As you get older, your ability to mineralize bones and do more depositing kind of goes down. Also, postmenopausal women have a much higher risk than men, as well as Caucasian women have a much higher risk. Sex hormones do help you to maintain bone density as you go along. So estrogen and testosterone do help you to maintain that bone density. In fact, testosterone actually increases bone density quite a bit versus estrogen. So men are much, much less likely to develop this because of those protective effects of osteoporosis. Now, some things we can do ourselves, right? There are some factors that we can get rid of ourselves. So just providing your body with exercise, having impact the bone actually helps to harden that bone and reduces your risk of developing osteoporosis. Having enough calcium in your diet, having enough protein in your diet, not smoking. Now, genetics you can't really affect, at least not now, right? Maybe in the future we may be able to affect it a little bit more, but right now you can't. So some other conditions like hypothyroidism or diabetes and consumption of large amounts of alcohol or certain medications can actually increase the chance of you developing osteoporosis. Now, there are some drugs out there that can help you to slow the osteoporotic process. One is just by just taking more calcium or vitamin D supplements, doing exercise, but there are also other things that can help as well, like hormone replacement. But with that always comes a risk associated with those hormones. And even with these drugs like bisphosphonates, right? They decrease that osteoclast activity and the amount of them. So that would kind of reverse that osteoporotic condition, but it isn't a end all be all. You do still need that remodeling to go on. So you just want to kind of reduce the activity and reduce the amount so that you don't have the ill effects of this. Now, another disease that actually can come from abnormal bone growth, which is quite interesting to me, is something that's called Paget's disease, right? And what happens with this is we get an increase in the amount of spongy bone to compact bone that we're laying down. So this is occurring because of the decreasing amount of mineralization. And we also have haphazard growth of bone. Osteoclast activity goes down and osteoblast activity remains the same. So this means we're laying down more bone than we're breaking down, which means we may have growths on areas of our bone that we wouldn't normally have. Now, it isn't totally understood why this occurs, but it may be tied to some viral agent that may cause these conditions to occur. Now, I really want you to study this material and understand this material. So as we move on to the next section, which we've discussed the naming of bones, right? All of this can kind of go into that next chapter so you can get a really deep understanding of how bones operate.